Hi everyone, in this video we are going to be looking at some differentiation as it applies to curves and functions and finding out more about what curves look like and maximum and minimum points and things like that. So firstly we should understand that calculus is going to help us because we know that the derivative is telling us the slope of a curve at any point along the curve. So there's interesting things going on when the slope is 0. And you can see in these examples here that we've either got one of three things. When the slope is 0, we've either got a minimum point, a maximum point, or what I call a stationary point of inflection, where the slope of the curve is instantaneously equal to 0. So one of those three things is going on if the slope is 0. Now this is important if we start to get into some applications where we've modeled a function and we might be the cost of us producing certain items or the profit. Again, knowing where we've got maximum and minimum of those things is really important and useful. But let's apply this one to, we're just going to be looking at graphs. So just to be aware, as we get a minimum point, you can see that the slopes, let's just focus on this one, the slopes of the curve, we go from negative, then we've got 0, and then we're going around to positive. So all during that time, the derivative is increasing from negative values to positive values. And the opposite thing's going on for maximum points. We've got a positive derivative, so there's a slope of 2, 1, a half, 0, negative a half, negative 1, negative 2, etc. So all of these times here, the value of the derivative is decreasing. So that might give us a clue about what the second derivative might do, might help us find it, but we won't go into that now. Let's have a look at this example. We've got a function, a quadratic function, and we want to use differentiation to determine the nature and location of any stationary points. Okay, so let's just make sure that we highlight that word stationary points and know that that means where the derivative is equal to 0. That's the definition of what a stationary point is. The derivative is equal to 0. And I've just shown that we've got three kinds of stationary points. So, or you could say dy dx is equal to 0 in this case. So, in this case here, dy dx, y dash for short, is 2x plus 6. And we want to know when that is equal to 0. So this is a pretty easy one. We get x equals negative 3. So negative 3 is the value of the stationary point for the x value anyway, but of course we want the coordinates, so we want a y value. To find our y value, we need to substitute that value of x back into the original equation. So the y value is negative 3 squared plus 6 times negative 3 take off 4. So you could do this on your calculator. Just be really careful about it. 9 minus 18 minus 4 is negative 13. So there's my answer to that one. The stationary point is negative 3, negative 13. So here's the graph of that function. We can see it's a quadratic. It's concave up the whole way. And there's only going to be one stationary point there. You can see at negative 3, negative 13 because it's a quadratic. A little bit more interesting when we get a cubic. So here we've got 2x cubed minus 6x squared. So we're going to go through all of these carefully and we're going to end up being able to sketch the graph of this function here. So firstly we want the coordinates of any points on the curve or on the graph where the function cuts the y-axis. A function goes through the y-axis when x is equal to 0. So in this case here, 2 times 0 cubed minus 6 times 0 squared is 0. So therefore we know that this thing here goes through 0, 0, and that's the only point that it goes through the y-axis. Part B, the coordinates of any points of the graph function touches or cuts through the x-axis. Okay, that happens when y is equal to 0. So we want to solve 2x cubed minus 6x squared equals 0. Alright, common factor here, 2 and 6, the common factor is 2, x cubed and x squared, common factor is x squared. 2x squared times x gives us 2x cubed, and 2x squared times 3 gives us 6x squared. Okay, you can check that by expanding those two there. That gives you the same thing. Yep, that's correct. Alright, cool. So our values of x, 2x squared is equal to 0 when x is equal to 0, and x minus 3 is equal to 0 when x is equal to 3. Alright, so that's what we wanted the coordinates. So the question is asking us for the coordinates. So I'm going to be good here and say the coordinates are 0, 0, which we got from the last one, and 3, 0. These were x-intercepts. So 0, 0 and 3, 0 are what we're after. C. C asks the behavior of the function as x tends to plus or minus infinity. Let's look at this thing. 2x cubed minus 6x squared. Okay, when x gets really, really big, the term that dominates here is going to be the x cubed term. So I know that as x gets really, really big, subtracting off the 6 lots of x squared is going to pale into significance next to cubing this really, really big number. So it's this term here that's really going to dominate, the 2x cubed term. So I know that when x gets really, really big, y is going to go off to infinity. Similarly, if we consider big negative values of x, same thing. This term here is going to be the dominant term, and I know when x is really big and negative and I cube it, I'm going to get a really big negative number. So y is going to head off to negative infinity. Okay, part D is where the calculus stuff comes in now. We want to know the nature and location of any stationary points. So we want to know the points where dy dx is equal to 0. Now it does ask us for the nature and location. Nature just means are they a maximum point, a minimum point, or a point of inflection? And the location, I think it should really say the coordinates. So we want to get the y coordinate as well. Okay, so let's do the derivative. Here it is 6x squared minus 12x. And we want to know when that's equal to 0. Again, some good factorising will make this a lot easier for you. Although I guess you could get your calculator out here, but I think it's even quicker for me to do this. Right? X equals 0 or x equals 2. When x equals 0, we know y equals 0. We've already come across that point. When x equals 2, I'd have to substitute that back into the original equation. Y is 2x cubed minus 6x squared. So we've got 8 times 2, we've got 16 minus 24, negative 8 for our y values. So the 2 points are 0, 0 and 2, negative 8. Alright, now we've found where they are. We want to know what kind of stationary value are they. Alright, well let's look at these points. So I'm just going to put them on a number line here. We've got x equals 0 and x equals 2. And what I'm going to do is just look at the derivative either side of these points. So for example, when I look at x equals negative 0.1, or a value of x, I guess we could go over negative 1. And what's going on with the derivative at negative 1? So if we look up here, here is the expression for the derivative. When x is negative 1, I get this, 12 times negative 1. So I've got 6 plus 12, 18. That's positive. So the derivative is positive before 0. If I look at the values of x between 0 and 2, so for example, let's look at 1. 6 times 1 squared minus 12 times 1. We get 6 minus 12 is negative 6. So the value is negative. So we're going up. Positive slope there. We know that the derivative is 0 at 0, and then it's going down. We know the derivative is 0 at 2. And you guessed it, when we put in a number like 3, we're going to get a positive number. Remember, we're substituting the numbers here into the derivative. So it's going up. So drawing this little diagram here gives me a real good idea of what the shape is going to be of this thing. And it does answer the question of what kind of points have we got. I can see that 0, 0 is a maximum value, just looking at the diagram, and 2 minus 8 is a minimum. Now that's sufficient. The word that I perhaps should be using in here is local. I should really drop those words in there because they're not the absolute maximum and minimum values of this function. They're just the minimum and maximum values in that area of the graph. If we have a look at the sketch of this graph, you can see here we've got 0, 0. It's just touching there. And then we've got 2, negative 8 down here. One's a maximum, one's a minimum. You can see if I put in a value like x equals 4, we get a much bigger value of the function way up here somewhere. Much bigger value than this. So we can't say that this value here is the absolute maximum of the function. Just what we call a local maximum. And similarly for 2, a local minimum. Okay, let's just deal with that idea in this last question here. Use calculus and algebra to determine the coordinates and nature of any stationary points on that graph, hence determine the maximum value of f of x for x between 0 and 7 and negative 2 to 7. Okay, so the basic part here is using calculus to find the stationary points. So f dash x here, 18x minus 3x squared minus 15. Okay, that's the derivative, and we want to know when that's equal to 0. So now we've got the derivative, we want to find when that derivative is equal to 0. I can see there's a common factor of 3 here, which is really going to help us. So 6x minus x squared minus 5 is equal to 0. And making it even easier, x squared minus 6x plus 5 equals 0. I think making the x squared term positive just makes it easier for us to factorise. So let's do that. Let's see if it factorises. You could use a quadratic formula here, but in this case here it works out nicely. We want two numbers that times to give me 5, add to give me negative 6. So it's x minus 5, x minus 1. So the x values here are x equals 1 or 5. We want the coordinates, so we also want the y value. So I then have to substitute 1 back into the original equation here. So I want f of 1 really. 9 times 1 squared minus 1 cubed minus 15 times 1 plus 11. And that gives you 4. And then you substitute 5 in there back into the original equation. And you can check that gives you 36. So the two stationary points here are 1, 4 and 5, 36. There are our two stationary values. Now what kind of stationary values? That's what this question here is asking. The nature of the stationary values. Again, I'm going to just draw a little line here with my x values for the derivative, 1 and 5, and I'm going to see what's going on. Remember, this is the slope of the curve. So I know the slope is 0 here and here. What's going on before 5? So what's going on at 0? Let's look at our derivative. Remember, our derivative is this thing right here. Okay. So what's the slope when x equals 0? If I put 0 in there, I get negative 15. So it's negative, it's going down. Put in a value like 2 into there. 18 times 2 minus 3 times 2 squared minus 15. You'll find you get a positive number. Doesn't matter what number it is, as long as you know it's positive. And similarly for numbers bigger than 5, you get a negative number. So it's going down. So I can see that 1, 4 is a local minimum. And 536 is a local maximum value. Cool. Now the question here says, hence determine the maximum value of the function for between 0 and 7. Okay, so we want to know the global maximum, the absolute maximum value for between 0 and 7. So if we think about the graph here, this thing is going down. It's got a minimum point at 1, 4 and a maximum point at 536. So because this is a negative x cubed graph, it's going to be coming down like this, Go up there like that, then down like this, and then down like that. Something like this. Okay, so what the question's saying is between 0 and, here's 5 here, between 0 and 7, what is the maximum value, the biggest possible value that we can get? Well, I can see for that region there that the curve right at 0, we should really know what this point here is. Does this get higher than this point here over here? So I'm going to work out what f of 0 is. So substituting 0 into the equation gives me 11. So this is at 11. So I can see that in this region between 0 and 7, the most we ever get, the highest point we ever get, is over here at 36. So therefore, my answer for A is the maximum value is 36. Just kind of considering the graph. Okay, for B, what's the maximum value between -2 and 7? Okay, if we go right back here to -2 on the graph, does this point up here get higher than 36? So f of -2. So again, we're substituting -2 back into the original equation here. That's this thing here. 9 times -2 squared minus -2 cubed minus 15 times -2 plus 11. So you've got to do that on your calculator. So I've done that. I'll chuck in -2 and I'm getting 85 as my answer. So it's actually way up there. So between x values of -2 and 7, the biggest value is now 85. Okay. Max value for -2 to 7 is 85. Here's a nicer picture of the graph.